Welcome back, Haskell lovers and Haskell curiouses. I hope you're ready because this talk is happening one way and another. Excuse the pun. Please join me in welcoming our next speaker, Dmitrii Kovanikov. I first met Dmitrii at the Singapore Haskell meetup a couple of years back when he presented whatever the latest amazing thing Kodak made. Dmitrii is one half of the very well-loved Kodak, known for such things as Reload, Colog, Stan, etc. As you can see from a lot of the work that Kodak puts out, Dmitrii loves to make hard-to-understand topics accessible to everyone. And a running theme that I also noticed in his work is practical utility. I have a feeling that today's talk will also be along those lines. So Dmitrii informed me that he'd prefer to answer questions later after the talk in the Q&A room, but I'll keep collecting your questions in Discord as well. All right, and with that, I hand it over to you, Dmitrii.
Hi, everyone. I'm Dmitrii. Thank you for this wonderful introduction, Kartik. I'm really happy to be in the happy room. And let's talk about bidirectional conversion today, and my talk, one way and another. So a few words about me. I'm currently working as a quantitative developer at Standard Chapter Bank, where we write Haskell. In my free time, I do a lot of open source in Kodak, and I previously been a lecturer at the university as a Haskell, and you can find me as such in different social media. So what this talk is going to be about? First, we're going to introduce some basic definitions, so we make sure that we are on the same page about serialization and all this stuff. Then we will talk about unidirectional conversion, the way how it's usually done and most of the time. And then I'm going to talk more about bidirectional conversion, the new approach, less explored approach. And we'll talk about the TOML library, a library that implements this approach for parsing the TOML format. And in the end, if we have time, I will discuss possible future improvements to this library. So this talk is not going to be a tutorial on TOML. I think we did a good job of documenting all the stuff, but it's more about motivation for bidirectional conversion, why you should care about this approach, how it solves some of the common problems of unidirectional conversion, and what was the challenges. And I will try to explain some of the abstractions that were used to build the library. So this talk is a little bit on in the intermediate level, and at some point it can become a little bit hardcore, but we will start smoothly, and I will try to explain everything in the beginner-friendly way. So bear with me. So first, when we talk about conversion, we usually talk about conversion in two directions, like decoding and encoding. And I used to always mix these terms a lot, but after working on serialization library for 3 years, I don't mix them up. So that's one way to understand them. But you can see a lot of synonyms and alternative names for these things. But basically, when you decode or you parse, you convert data from some format which has less structure to a format which has more structure. So, for example, text, and text can be arbitrary, it can be JSON, it can be a poem, and anything else. But then you convert it, for example, to some data type, and you understand more about the structure of this text. And this is basically what decoding and parsing. And on the other direction is when you have the structured type and you want to convert back to less structured representation. And you may want to do this because, for example, if you want to communicate with other systems, other languages, they don't understand your types, but they can understand this less structured format. So you may want to convert them to tell them. Or, for example, if things can store in computer at like bits, ones and zeros, but then you want to show them to a human and in a more accessible way. And usually when we work with parsing and decoding, we have this intermediate representation. So you can treat like parsing and decoding as synonyms, but I prefer to distinguish those terms. And for me, for example, when you have a text, some structural, some less, not structural, some like arbitrary form data. It can be in a file or maybe some field in a web form. And usually when you want to decode some information from this text, you convert it to some AST, some more structured information, but it's still generic enough to cover all such objects. And then we decode our types from this AST. So this approach usually happens when you want to decode some formats like JSON or YAML. Often you can skip this AST part if you want to just extract only relevant parts of your data types from the text directly, and you can just go direct to types. So in this case, parsing and decoding are kind of the same. But if we have this intermediate representation, I prefer to think about different terms. And we can go the other direction. If we convert our types to this structured representation to AST, we do encoding of our types, and then we pretty print to some format less structured. And this is how it's usually done. You can see that the data can flow in both directions. And what we really want to capture is how to do this nicely. So here are a few examples of decoding and parsing. For example, CLI arguments. When you write commands in terminal, you specify just a string in special format with dashes and stuff. And there you specify flags and other arguments. But in reality, it then converts to data types like booleans, integers, strings, list of stuff, and other stuff. So we see how we move from this text, less structured information, to some form where we know more about the way. There are a bunch of common formats like CSV, JSON, YAML, and TOML, from which used to define configurations or APIs, and we want to convert from them to our types so we can actually process them and analyze and do some stuff. A more complicated example is programming languages. So unless you are using some really modern paradigms and really modern languages, you still write programs as text. This can be arbitrary text, but it should satisfy rules of some specific programming language if you write in it. And it's a mind blowing that you just write text, but then a compiler can actually translate it to some very complicated form to AST, and then can perform various analyses, like check if the program makes sense, if it type checks, and then it can perform optimizations, like you wrote some code, but then compiler can make it run faster, and it can actually run it. So it can convert just text to something runnable. That's pretty nice. And it's not only about textual data, it's also about binary. So for example, if you transfer data over the network, like in some application format like protocol buffers, or in more low-level format like TCP, HTTP, you transfer maybe some data, and it could be binary data, and then you decode it, you try to parse it, you try to convert from this compact form to a more to types with which we can work. And standard example of like decoding type class in the Haskell ecosystem is a read type class, which basically gives you a function to convert from string to a type native. And examples of one can be like, think of in reversed ways. So for example, you may want to output some of the data types in a colored way to a terminal with spinners and helpful links and fancy Unicode characters to make it really understandable for humans to read this output. This is where you can like pretty print to terminal, and even the same format like CSV and TOML, you may want not only to read them to data types and process, but you may also want to output them to other systems, to other machines. And programming languages analog of parsing is formatting. So when you just process your programming language and you output it in some uniform way, not necessarily pretty, but it should satisfy some machine-defined rules. And well, you don't use formatting for pretty output, you just to have consistent output. And you also can output encode as the binary data if you want to transfer to some services, and like in compact form. But again, encoding and pretty printing is not always about compact form or some like really compressed representation. You may want to provide more information, like basic printing of data types or other stuff to terminal. So it will be more verbose, it will take more space, but it will be easier to understand it. So this is one way how decoding can be helpful. And again, a simple Haskell example of such a type class is a show where you just convert any data type to a string automatically. So let's talk about unidirectional conversion first. So how usually it happens when you have some data types, you define them, and then you want to convert them like from types from your programming language to some representation. How you usually do? So you write some code which tells how those types should translate to this representation. It can be like less structured representation, AST, which some library can convert you to text, or you can translate directly to text. And you write this definition in one place, like for example, if you want to encode to some format, but then you realize, oh, I actually want to get my data types from that another format. I don't only want to convert to it, I also want to convert from it. So in some other place, probably far away from the initial place, but maybe near, you can just write another function code, and it just two pieces of code hanging around that should be connected somehow, but they're not connected. They're written in different places. And in Haskell, we have such nice things as deriving, and using like generic deriving or deriving via, you can reduce this boilerplate, but it's still written like in different places, but it's more just on the library level. So the library just handles it, but you just rely on that the library really works. So what are the benefits of this traditional approach? First, sometimes, or maybe often, you need only one direction. You don't need to convert from some format. You only want to output to this particular format. For example, if you're writing a CLI tool and you want to produce a machine readable output, you don't really need to parse it. You just want to output it so other tools, other consumers can read it and they can parse and process and somehow analyze your tool. So you don't really need both directions. Moreover, it can be really difficult sometimes to go like in both directions. So it just might be not an option. You may do something another. It's also like a simpler model. So, okay, I have this format and I have these types. So I want to go from this place to this. Okay, I just write code how to go from this place to this. So it makes sense. You just like a journey from point A to point B. And if you want to go backwards, okay, now I have these types, and now I need to think only how to go in another direction. So I can just write the correspondence between the type and how to go. So it's a one unidirectional flow. And moreover, this is a standard approach, very established for a very long time, not only in Haskell, in other languages as well. And there are a lot of best practices and things how to avoid various pitfalls and very developed infrastructure and functions. So it's really modern, and you will probably solve all your problems with this approach. But you might not solve them ideally because this approach has some drawbacks. First of all, your conversions, they can diverge. So you wrote like conversion in one direction, and then you wrote in another, and then you decided, okay, our consumers want to do other stuff, so let's just output this not as a string, but like maybe an object or something like that. But then you forgot to update how you parse, because often when you have a type, you want to have a uniform format in both ways, like how you encode in format, and you also want to decode from the same format, usually. Not always. Sometimes you may want to decode from a more flexible format if you consume some API, which can have versions and they can produce out to different formats. You can be more flexible on decoding, but on encoding, usually you don't output like relevant data or like in random format. So this can diverge. And there are ways to solve this problem. First of all, it's like writing tests and make in Haskell, you can write property-based round-trip test where you can just generate random value, you convert it to some format, and then you convert it back. And then you can make sure that your instances are actually consistent with each other. But when you see it code, it can be, if you try to review code, try to analyze, it can be difficult to see like the correspondence. Like if functions use different, this conversion use different functions, different operators, and different styles, and some logic, some conventions have more logic, like not to parse more flexible formats, maybe difficult to see how they correspond, and they just not in the same place. And by default, by design, this approach of unidirectional convention is incorrect by construction. So you write in one way, you write one convention somehow how you want, and then in another direction, you start from empty function, and the only way to make it correct is just like to remember how you wrote it, but nothing stops you from writing something different. So you just really need to make sure that it's consistent, and then you do tests, like as I mentioned, property-based round-trip tests. You also really want to have some golden tests, especially if you provide API, because okay, in your data type you changed one field in record from like integer to string, and your property-based tests, you patch the conversion, yeah, and your property-based tests pass, because yeah, sure, like you convert to string and then back, we can parse it. But then users external to your API, for all of them, it now fails because they expected to see int, but now you give them string, and they're like, what? And yeah, you really need to have some golden test, and this is like some work to make sure that your conversion works. And what I want to say is that there is a better way, or at least we should strive for solving this problem in a better way. And this better way is a bidirectional conversion. And in bidirectional conversion, I mean when you specify in the same place how your user types correspond to values in this another format to specific parts of it. So you don't need to worry about the files. You have one place, just like bidirectional arrow, just say like, I want to connect those two parts. I don't want to write separate conversion in one direction and in separate place conversion in another direction. I just want to connect them and like, please make sure that they work. And when Haskell developers hear about bidirectional conversion both ways, a common topic of isomorphism can come to mind. And in this context, isomorphism is not about web applications that can run on both server and client. It's about conversion in both direction, preserving like the structure value, and you can convert in both ways. This is what basically isomorphism means. But it doesn't work for decoding, for our like serialization problem and encoding, because isomorphisms supposed to like always convert and then always produce a correspondence between values. But when we decode values from some format, we may have errors. For example, if the format is incorrect, it has some maybe types invalid format, or we expect to see something different, or some other tool or people gave us an incorrect format, so we can see errors. And moreover, if we convert from our data type to this format, we also may like produce errors. We may not always convert to this expected format if our types like not what the format expects. And this can be illustrated by this diagram. So we have values of type A, and you want to convert them bidirectionally between values of type B. So, and we can have these errors, values of type E. And from some elements, we cannot convert. We just go to errors, and in another direction, we also go to some another errors. But important part here is that if you go from A to B, we also should go from B to the same A. It's important to go back not only to the same type that it was, but also to the same value. So we really want to preserve this structure of like this property of isomorphism when we map same values back and forth again. And a simple example of bidirectional conversion that can fail in both ways is conversion between int and natural. So int is a bounded type, and natural is an unbounded type for non-negative values. And when we convert from int to natural, we can fail because int can be negative and natural cannot. Natural should be 0 or a positive number. So we may fail when we convert from int to natural. But on the other hand, we may fail when we convert from natural to int, because natural can be arbitrarily big, and int is only like 64 bits. It cannot hold all possible numbers. So really big numbers we can convert and we should fail. So this is an example of where we can fail. And this is a nice diagram, but how can we represent it in Haskell? And in Haskell, we can represent this as this bmap type. It's short for bidirectional mapping. And this is a data type which has 3 type parameters: E for errors, and A and B for 2 arbitrary values between which we want to convert. And we have 2 functions like forward, when we go from A to either error or B. So we have A and we can get either error if we cannot convert this value, or we can get a B. And we can go back from B to A. And you cannot specify this in types, but as I mentioned before, we need really this property if you go from A to B, and then you with forward. And then when you apply backward, we really want to get the same A. And in this particular code, we're using the same error type for conversion in both ways. But in reality, nothing stops you from having 2 type parameters, E1 and E2, and have different errors for conversion. You just do this for simplicity, because we don't really care about so much flexibility. And the nice thing about this type is that it's actually category. So yeah, category theorists can be really happy in the happy room. So which means that we can implement an instance of category type class for the bmap, and we have an ID, which means that we can go from we can convert element to itself in both directions. Of course, we can just go from it and to itself by wrapping in right. We can go back also by wrapping in right. So ID is really straightforward. And what's more important, we can compose bidirectional conversion. So if we can go between A and B in both ways, and if we can go from B to C in both ways, then yeah, we can go from A to C in both ways, just move. Probably, maybe we can go to error on the way, but still it should be possible. And the composition is also pretty straightforward. When we go forward, we go from A to B forward, and then we go from B to C forward. And when we go, if we want to go in backward directions, that's written. We go backward from C to B, and then we go backward from A to B. And voila, we have a conversion. In the implementation, we use this fish operators, because we don't really have just functions from A to B, we have functions from A to either. So we really want to have this monadic handling of errors. And this is how this composition can be explained on a diagram. If you don't like category theory, you can call this like a pipey composition, when you just attach pipes to each other and you need to make sure that the ends fit each other. But yeah, as I said, we have values of type A, we go to B, and we go to C, following arrows. And if you want to go in backwards direction, we can go from C to B and from B to A. At any point, we can fail to error. The error type is shared for all of the conversions. It's like this common part, but it should be possible to move in all directions following errors. And it's really nice property. So we can convert between values in different formats. And it's nice because when we develop applications or just parse applications, we really want to care about composability. We really want to make sure that we create some small parts, and then we can combine them together to some like bigger part to solve our problems. And it's nice that we have this category instance that we can compose. But we, I call this pipey composition, but we also want, which I call squashy composition, is it's nice to go from one direction to another. For example, we have text, we can go to natural, and then we can go to byte string, and maybe to some data type, and then go backwards. But what we also want is that composition in another dimension, I would would say. So for example, we have custom data types, records, and they have several fields. And we want to convert those several fields simultaneously, not between them, but in parallel. And the simple example is like this Squashy function. So we have a bidirectional conversion between A and B, and we have a bidirectional conversion between X and Y. And what we really want to convert between a pair of A and X and a pair of B and Y. And it's not a difficult function. Yeah, it's really easy to implement. And you can do this if you want to practice this bidirectional conversion. So we just convert in parallel our records. But and we can go with this approach, but it doesn't really help us with solving the composition problem, because like records can have arbitrary like size, and we need to implement like squashes for all sizes of tuples that we care. And then we also need to manually convert between our data types to these tuples and back again if we really want to convert. And it can become really messy. And usually we are solving this problem with functors, applicatives, and monads, but our B map type is not a functor, and it cannot be a functor. More important, well, not functor that we need. We can functor on errors, but it wasn't really helpful. So this is because both variables A and B, they happen in both like covariant and contravariant positions. So that's why it cannot be a functor. But we really want applicative. So here it comes like to problems that we want like familiar applicative interface. And when you think about this, like, okay, we need some sort of monad, some like contextual box, and how we can design this like in a similar way data type. So here's data type that doesn't work, but it gives an idea of what we want. So we want some codec, which has this, which has two parameters, like some monad, in which we can have our conversions, and it's codec for values A. For example, it can produce values of type A, which we then will combine and with applicative interface. And we have this codec read function, which just in this monad, and it parses values of type A. And the codec write function, it takes A and it somehow puts it into M monad. So for example, let's say M stores our AST, intermediate representation, in a context inside like a state monad, something like that. And we just convert A to some uniform format and push it to M. And it should store here. But this type still cannot be a functor for the same reason, because a type variable involves covariant and contravariant position. So here's how the codec type actually looks like. It's a little bit scary. It has now 4 type variables. Don't worry now, we will simplify it later. But this is how the original work looks like. We now have 2 monads, R and W, and we use different monads for reading and outputting. And the reason for this, because when you read, you don't actually want to change the context. You want to have some like reader monad, which stores AST in its context and doesn't change it. But writer, you really want to change when you output, when you push back your values to the monadic context, you really want to change it. So W is like writer or state monad. And we have these 2 type variables, input and output. It's a bidirectional conversion, and we get output. And when we write, we get some input and write it to output. But it's a little bit tricky. And the I type variable, it's actually fake. So it's always should be equal to O, but it's like this fancy trick. We introduce a separate type variable, so we can have the O type variable only in the end, like in covariant position, and we can implement functor and applicative and monad instances and what's not. But we will always, in our types, say that I is the same as O. So this is like a trick, like to full type system, so we can implement all required instances. But you can think that the I parameter will be always the same as O. So yeah, that can be a little bit difficult to see. It's not a standard way to solve problems. And yeah, we have this codec, which we'll use in applicative fashion. But the nice thing is that we can go from B map to codec the details of the implementation are left out. But with BMap, we have this like modular compositional pipes for individual values. So we can build like bidirectional conversion between different values like text, byte string, naturals, and all the stuff. So we build them. But we then use Codec to compose all this conversion in a single record in a value data type. So we can have actually to parse them simultaneously or like in parallel, if you prefer. So we have this all fancy abstractions, and it looks nice on paper, but how does it actually behave in theory, in practice? And for this, we need to solve some real-world practical problems, and we need to choose some format, and we then need to try to apply all this instruction. And here comes the TOML. This is a Haskell library for bidirectional TOML serialization. We choose a TOML format. And a little bit of history about TOML. It appeared in 2018. So it's like 3 years old library. And at that time, when I was working on TOML, I really wanted to use TOML as a configuration format. And I wanted, for my use case, my application, I needed pretty printing. But none of the libraries back then provided that functionality. For example, the popular library HTOML still has open pull request about pretty printing. And yeah, we decided to, and it didn't really move anywhere. And also HTOML based on ASO, like it uses type classes for JSON to represent TOML. And we want to have a more lightweight library with pretty printing, and we also want to explore this bidirectional serialization. We learned about it back at that time. So this is how the library appeared. And a little bit about the TOML format itself. So TOML is a format for application configuration, for static configuration. It's supposed to be a replacement for YAML because it's much simpler. Its specification is really, really small. You can like read it in hour less to understand how the format works. It's basically just a key value mapping with some tables. So we have like keys, values like strings, booleans, like arrays of some integers, just integers. You have these tables, which can be like understood as records. And you have list, is this double square bracket. It's like a list of records. You can see that in this case, we have like a list of some types. You can have guest ID, or you can have like login and create. This is basically how the TOML format looks like. So now a few words about TOML itself. TOML supports TOML specification version 0.5.0. TOML spec already has 1.0 version, so it finally reached 1.0 milestone, but they changed a lot of things, and it will require a lot of engineering work to support that in a TOML library. And TOML already used by 12 packages from package. It's not a big number, but because mostly you use static configurations not in libraries, but in applications. And you don't upload your applications to package usually. So actually TOML used in more applications, and we use it in production. So it works. It has it took design decisions to have a like a value-based approach, because with the classes you really want to have a conversion like the same way. But as we said, we can convert from values in different ways. We can go from text in one way or another. We decided to go with value-based approach, but the library still supports generics. And if you have really standard types, if you really want like really basic stuff for prototyping, or want to code something quickly, you can just don't care about all the stuff and derive all generically and get all the decoders for you out of the box. TOML has a blog post tutorial which describes its internal architecture, and now, thanks to Haskell Lab, it also has the tutorial in the form of this talk. So library has really lots of code, like 2,500 lines of source code. It's developed over the time, and it's changed a lot. It has more than 3,600 lines of documentation, even more. So we really spend a lot of time writing documentation, examples, tutorials, doc tests, stuff like that. It has even lots of tests, because we want to make sure that when you compose parts of the TOML, it really works as expected. So we make sure that all conversions are work, and it has really nice structures of modules and modularized definitions. So let's now talk about a little bit of internals. And how all these abstractions work? First, like there was this complicated representation with 4 type variables, and we used it. This is how it was in TOML before. But then we wanted to use like deriving VM and other stuff, and turned out it wasn't really possible. And it could be solved if GHC had a feature of so-called higher order roles. It's a really complicated feature. But we decided that like it's still not accepted, not implemented the proposal, but we decided that we will simplify our data type to achieve like practical needs. And just remind, this is how the data type looks like. We have monads, R and W. And the first thing, like, let's get rid of this R monad and use just reader. So we know that it will be always a reader. In our case, let's just use it reader parameterized by AST, like some AST format. And the same goes for W monad. We just replace it with state because we will know the state needs somehow push values inside. So we'll use the state monad. And now, okay, we know that actually we also need to produce some errors. When we decode, we cannot just always give A when we decode. We need some errors. So we use either, and we introduce type variable for errors. So now we have this monad transformer stack for decoding, and the same goes for encoding. In encoding, we don't really care about errors that much. You could care, but we don't, because you either push value if you can encode to the AST, or you don't. And there is not much in our practice which should happen. So we just use maybe T, because if you can, there is no value to output if it cannot be pushed. But like now we have this probably even more complicated type. It still has 4 type variables, but now it has also monad transformers, and it becomes really scary. So let's simplify it. First, we will get rid of reader T, like it's just a function from AST. And now you can actually see some similarities with the B map. Now we have like AST, and we convert it to either error and our value O, something like that. Yeah, it became much simpler. And we also unwrap the state. So now it makes, you can see the difference between the B map. We have like input value, we have AST, and we produce some, maybe produce some output value. And we also produce new AST that we need to return, which updated values. And if you want to have a general abstraction, you can stop at this point. But in TOML, we know that, okay, our AST is this like TOML type. We will work with TOML. So let's just use a specific type and make things simpler. And we also know that our errors is TOML errors. Like it cannot be JSON errors. So let's just specify it and make the type simpler. And the one last step is that we used either before, but in last major version of TOML, we decided to use validation and to combine all errors. And in decoding, it was really nice to get all the errors. So this is how the final data type works. It has only 2 type variables. And I hope you now see how this abstraction maybe makes sense. And as I said, in reality, we always specify the same I and O. So actual TOML codec is just the codec where you have the same values for input and output. And nice things about codec, we now actually can implement all the instances like counter-applicative and alternative. We cannot implement the monad because we are using validation now. And we realize that we don't really need monad for TOML. You may want to need it in like in binary serialization. In binary, it's very common when you just first part, it's just the fixed size integer that tells how many elements in an array, then you parse it, then you parse that many elements, stuff like that. But in TOML, you don't have that. We still can benefit from the selective instance, for example, if you want to parse version data, but it's totally possible to implement it. And we can implement profunctor instance. Actually, the codec is a profunctor. And we don't have the instance because, as I said, we want to keep the library lightweight, and profunctor brings a lot of stuff, but we can implement all the combinators and we can use them. So this is how a quick look how the library uses it. We have like record with 2 fields. And yeah, in the codec, you just specify a TOML codec of your data type. Inside the text, we get it in the TOML, it will be under key name, and it maps to this field. And we have integer, it has under the key age, and it maps to user age. So really not a lot of code, but we have the bidirectional conversion. We define this data type, and we now can convert both from TOML and to TOML. We can mention that the decoding of some types was a really difficult part, and we spent a lot of time brainstorming how to implement it properly. But we really wanted to use an alternative instance. And after we switched to validation selective, our package provides validation type, and in different alternative instance, we made it possible to use our bidirectional decoding for some types, but it was really like mind-blowing, and for a very long time we couldn't do this properly. So what are the benefits of this bidirectional approach? It's correct by construction. Well, if library has no bugs, but we do a lot of tests. So you just specify your decoder, and you have like conversion in both ways, and it's correct by construction. And you also have decoding and encoding out of the box. So for some simple case, you can write the same amount of code that you would write for unidirectional conversion, but you have conversion in both ways, and it could be really useful. And it's all in one place. You can really see this. The problem is this, it's difficult with this approach for non-trivial cases. So if it's something standard to trivial, and if library provides this combinator, then you are good, you are covered. But if it's something non-trivial and you really need to work with this internal IXT, it can become really messy, especially if you haven't worked with it a lot. And it's still like new and unfamiliar abstraction unexplored. So you already saw how many shapes it can take. It's probably not final form, it can be improved. So it still can be nice, but I think these problems can be solved because the more TOML develops, the more cases are covered, and the more documentation happens, the more people try to use this approach, the more familiar it becomes. So it's really a nice approach to solve these problems. And there are actually several libraries in Haskell and other languages. So there is a Codec library, which uses actually this polymorphic Codec monad, from which it was taken and inspired by which. And it provides like the bidirectional coding for the JSON for binary format. There is GG library for bidirectional JSON schema-based conversion. And at work, we use the schemas library. It's also bidirectional conversion between Haskell types and JSON, also based on schemas, but a slightly different approach. And in Elm, there is Elm JSON bidirectional library. It doesn't support the latest Elm compiler, but it gives you an example how you can implement this in a language without that classes, without these abstractions like pointer, objects, and monad. And of course, there is a pure script version like pure script Codec, which has this basic abstraction. And then there are other libraries that are built on top of this abstraction to provide JSON conversion and whatsoever. So what we really want in the future, so it looks all nice, but what can we improve? So one thing is that we want to have automatic examples. For example, we really often want, when we like parse some configuration to install applications, we really want to produce some default configuration, just output it to terminal, and we can just define it as a data type and use Codec to like generate an example. And it would be really nice. So people can like convert this config and just copy paste it and change only relevant parts. It's not a difficult thing, just some engineering work, but it would be really nice to have. We may want us to like think about format preserving bidirectional conversion. For example, with such configuration files, you may want to have some tools that change them automatically, and ideally they don't mess up the format entirely, but it may be difficult to do so. It will require entirely new AST, so it's really need to preserve all the comments and all the structure and all the commas. So it's really difficult and time-consuming engineering work. And moreover, when you convert to Haskell types, you lose all this information about formatting. So if you go back and you don't have this information, you like lose it. So it might be not good fit for bidirectional conversion, but maybe it's possible. It would be nice to explore. So another alternative thing it would be nice to explore is like this pipe decomposition for Codec. So Codec cannot have like lawful category instance, but it would be nice to have, for example, if you have bidirectional conversion between TOML and types, then you have between your types and JSON, you can automatically convert between TOML and JSON automatically, because basically this is what most of the programming, or at least for web backend application, does. You just take data from one format, push it to another, and go to the database and push it back to another, just basically transform between these data types. It'd be really nice to implement this composition. And moreover, maybe we can have some polymorphic codecs, like which can describe common structure of all schemas, because JSON and TOML and YAML, they somewhat similar. So maybe we can have a single codec, which can then be used for different languages. It would be really nice to have this, but it's just some things to think about. And that's all for me. Thank you for your time, and thank you for attending my talk.
Awesome. Thanks, Dmitrii. It was a lot of content. A lot of it kind of went above my head, but I think I understand where it's going. So if you have any questions, please join us in the Q&A room. Dmitrii will be waiting for your questions there. Don't be shy.
Yeah, see you there.